All right, welcome to session 3 of high performance LLMs from first principles. So it's always the goal is to achieve high performance on LLMs. And last week we thought about single chip performance. And this week I'm actually very, very excited. We're talking about multi-chip performance. And this is actually the heart of what makes JAX so special and so magical. So multi-chip performance. What do we mean by that? We're going to talk about, in this class, we're going to actually all three of these. We're going to program, we're going to write some JAX, hopefully. We're going to predict how long things should take, and then we're going to do some profiling, see how long things actually take, and see how it matches our expectations. I think this is probably going to end up an arc that will take a couple sessions to fully cover, but very, very excited about it. So as always, ask lots of questions, just start talking if things on your mind. So why do we train on multiple chips? There's really like a very simple reason, which is for training in particular. A training frontier model would take thousands of years on a single chip. So people are going to multi-chip training to be able to get these models trained in a reasonable amount of time. And then for inference, it's usually that latency. We want more chips because that allows us to give both better perf per dollar and also to give a lower latency solution. So we had a very simple system diagram that folks might remember from 2 weeks ago when we talked about this. We had a chip on the left that had compute and had a little bit of SRAM. And on the right, we had the memory, and we were able to analyze the rooflines of that system. So this week, it gets a little bit more complicated. So we have our system diagram for TPUs, and we have a bunch of different things going on. So on the left, we have the data center network. So that's how fast the host can see the network. This is what you normally think about when you think about the internet. Then we have the host. The host has a CPU and has RAM, the same way we had earlier. We have PCIe, which is how much bandwidth we have between the host and the chip. Then we have the chip, and this is the system we were talking about earlier. So what we have on the chip itself is actually kind of exactly what we're used to. And then additionally, we have the interchip interconnect. So this is how fast each chip can talk to its neighboring chips. And that's a thing that's probably a little foreign, right? Normally we talk over the internet, but here we have a very special, very fast private network. I find like these are kind of the way the specs are explained, and I find them like a little bit hard to understand. So I will jump us into a scale diagram of what's actually happening here that I actually find is a lot easier for us to reason about. So the bandwidth between the compute and the HBM is actually gigantic. The second largest is the interchip interconnect, so each chip is closer to its neighbors. And as we go further to the left, there's less and less bandwidth. So that a TPU can talk to the host at 64 gigabits per second. It can only talk to the data center network at 25 gigabits per second per chip because there are 4 chips per host. And then additionally, that SRAM we were talking about, we made such a big deal about the SRAM. We talked about it so much last time. It's almost like invisible in this new system. So helpful to think about the system like this can be really useful and really see kind of what's fast, what's slow. And I just wanted to spend just one more second talking about the private network. So for TPUs, we usually call it the interchip interconnect. For GPUs, they call it NVLink. And we have all these chips we want to have work together in a computation. And having the fast interconnect, we'll see, makes it a lot easier to get good performance.
Hey, so Rob, I have a quick question on the previous slide. You have the HBM to chip as 9.8 terabytes per second, but when we were looking at it last week, wasn't it 1.23 terabytes per second?
Yeah, I mean, that's a good call out. I should do everything consistently. So I have these all in gigabits per second, but probably I should just redo this slide and put into terabytes per second. Right, so those are the same, like 1.2 times 8 is 1.23 times 8 is about that 9.8 number.
Okay, thank you.
Good point. I think we can make that clear. Awesome. So in the first session, when we first talked about the matrix multipliers, what was going on that first within the LLM, we had kind of this picture. We have activations for a layer, we have weights, we multiply them, we get some output. So here we're going to go in just one level of detail more how we would do this on a multi-chip system. So the Google's answer, and the answer we use in JAX and PyTorch XLI, is GSPMD. It's an incredibly, incredibly beautiful answer. Very, very unique. So it uses XLA to do this. We tell the compiler to shard the matrices over different axes of our mesh, and each of the chips does the same computation. So here we have a particular sharding. We have green and blue, and we have two devices. And then this tensor, which is 2 by 2, we can imagine sharding any way of these three ways. So we can replicate it onto all the hosts, all the chips in yellow. We can put it onto the rows, or we can put it onto the columns. I'm going to just show just one more example. So this is a 4 by 3 matrix, and this one can be sharded in yellow. All the chips get all the data. It can be sharded by rows. So one chip takes the top 2 by 3, and one chip takes the bottom 2 by 3, and it can be sharded by columns. But because, again, 3 is not divisible by 2, sharding by columns isn't going to work here, because we would have to give the chips an uneven amount of data. So I think that that's like maybe makes sense to folks abstractly, but I thought it would be good to just like hop into a programming exercise when we can play this game, and let's see how things work. So I'm just going to really just code this up in JAX Live, and let's hope that I remember what I'm doing. Can folks see okay?
Yes.
Awesome. So we have JAX.devices, and we're going to call this thing my axis. So we're going to make a mesh. Actually, maybe even before we see this, let's think about what we've been doing in the past. So in the past, we've just been doing something like this: jax.numpy.ones, and we make some tensor. And if we interrogate this tensor, excuse me, what we'll see is this tensor actually exists on a single device. So our system. So let's look at a few things. So first, we have JAX.devices, which is telling us that we actually have 4 TPUs on this box that I'm programming. But this tensor that we have only is on 1 TPU. So that's not a good state of affairs. So what we want to do is figure out how to use all of the TPUs for our computations. So what I'm going to do is I'm going to create a mesh. Perfect. I'm going to create a sharding. And we're going to see what this is in a second. Hopefully I remember my syntax. Takes a mesh and partition spec. So we're going to actually just say my axis. Okay. And this is not going to work. So this is going to be a jax.sharding.partition spec. Perfect. And then hopefully we can jax.device put A onto our sharding and the sharding. And we can just run this code over here. Perfect. So now when we look at sharded A, okay, well, what happened? Well, A was 1000 by 24, sharded A is 1024. But the difference between them is actually sharded A dot devices should refer to all of our devices. Sharded A. Perfect. So we can actually go a little bit deeper. So there's jax.debug.visualize array sharding. Okay, so this is saying that A is fully on TPU 0. And now sharded A is now stacked because we sharded over the first axis. I'm going to actually just put this into our script. Okay. And this is saying that this tensor, we've chunked. So one of each of the chunks is on the horizontal axis is per tensor. If we do sharded A, we can actually go a little bit deeper. Let me just pull it up, sharded A. And I can never remember this, so I'll just pull it up. Sharded A dot addressable data. Addressable shards, I think is what we want. Wow, hard to have a type in. Okay, 0 dot data dot shape. Okay, so what we've actually seen is now this tensor, when we think of it as one tensor, is actually being represented as 4 tensors under the hood. So I'm going to put this all together here. And then let's ask ourselves some more questions about it. So this is going to be sharded a.shape. And then this one can be how big each of those shards is. And then we will just run this. And we should see this tensor is overall 1024 by 1024 tensor. And we can represent it actually underlyingly in memory as 256 by 1024. So I want to show people a number of additional cases here that I think are very, very interesting. But before we do that, I just wanted us to stop. Any questions, any thoughts about sharding before we hop into this in more detail? Dialogue flow.
Yeah, I just had a quick question. Like, we did not specify what axis we would be sharding, right? So there was some inference from Jack's side.
No, like, we definitely did, but we'll see now. That's a great question, though.
Okay.
We were very lackadaisical at how we did it. So yeah, which axis are we sharding over? That's a great question. We'll definitely answer that one.
Thanks.
Any more questions? Cool. So to answer the question here, why don't we give this, because it's actually a very important line of code, we can give it its own line, key spec, let's call it. Let's call it P for short. And if we just run it like this, okay, we sharded over the rows. Perfect. And now if we just switch to this, now we're saying to shard over the columns. Does that make sense? So there's a whole, basically the partition spec is being mapped onto our array, and we're sharding over the axis in the position we want. Hope that helps whoever's a dialog flow. So now I'm going to try to do something bad. So here I'm going to try to shard over the two axes of our array over the same physical axis. And I think you can see that there's no way to draw the picture, right? Because like this array, the underlying array can't be sharded over both axes. It just wouldn't make sense. There's no way to draw the picture. And presumably, Jax will complain to us. Okay, a single name sharding specification can map every best axis to at most one positional dimension, but it has duplicate entries for my axis. So it's saying that, okay, well, you can't shard the same tensor over 2 separate axes. So one other thing we can see is we can just put a none here, or we can put a none comma none. It doesn't really matter. And we should get, now again, fully replicated. So these are actually the 3 cases that are possible for a single tensor. We can shard over rows, we can shard over columns, or we can fully replicate it. I do want to show that there's actually a little bit more we can do here. So we can do my axis 1 and my axis 2. So now we can have 2 arrays in index. Now we can do np dot reshape. So we could say, Jax, I want you to make a 2 by 2 array here. Hoping that I'll get a hint from about interfaces here. Array like, okay, yeah, cool. My device, and then we'll put 2 by 2. Okay, and that'll be our mesh. And now, okay, well now we can run the same thing, and the data will be fully sharded. It will be fully replicated over all 4 dimensions. But we can go in here, my axis 2. And we should see now the data should be fully sharded. But now it's sharded spatially. So now it's represented as a 2 by 2. Alternatively, now in this 2 by 2 case, we can go do this. And now each shard will still get that same 512 by 512 chunk, but they get different 512 by 512 chunks. Another option is actually, we can say, actually form these two axes have them act like one axis, and then put a none on the second axis. And now they should stack vertically. Again, now it's 0, 2, 1, 3. While if we do it this way, we'll get a different vertical stack. So again, what we're doing is sharding the physical axis, the tensor's axis, different ways over the physical axis. And of course, we can do the same thing here. And we'll get now column shards coming out. And then the column shards will be 1024 by 256 because we're sharding over the second dimension. There's a final case we should talk about, which is we can do a partial replication. So if we shard only over my axis, 1, so now each of the chips should get a 1024 by 512 chunk. And the chips will each have 2 copies of it. So we see that here. The total size is still 1024 by 1024. And then the data shape is 1012. It's 1024 by 512. We've partially replicated each of these tensors. Cool. I think we'll quickly jump into doing some computations with them just to show that we do know how to compute on the differently sharded tensors. And then we can analyze the system a little bit more carefully. Any more questions on how this is laid out? The goal here should be that when you see the partition stack, you should be able to guess what the picture will look like. That's really what I'm hoping folks will be able to do. So if that kind of isn't totally clear to you, I'd love to have people ask questions, and we can do a few more cases. I think Natalia, your hand was up first.
So for the physical mesh changes, from just 4 devices to 2 x 2 devices, right? Does it change the interconnects? How does it?
No, that's a really, really good question, but it's not changing the interconnect. So maybe I could just, I wonder if I could quickly, basically, the underlying system does actually look like this. So you can think about it as being those 2 different ways, and they both are legit. So I'm going to put 4 colors on them. And so that's how the actual system that I'm on looks like. And you can think about it as being 2 by 2, or you can think about it as being a 4 by 1 with a wraparound.
So it's physically no difference in both.
There's physically no difference, definitely. But there's 2 different and legitimate ways of thinking about the system. Rand?
Yeah, I have a question about the sharding. So I'm not sure if you will cover in the later. So you showed us a couple ways of sharding, but what's the best practice when we sharding the data? So is there any
Yeah, we'll analyze that in great detail. That's a great question, Rand.
Thank you.
Vaibhav?
So one thing that did not make direct sense to me was that when we were sharding both the axes of a tensor on a single mesh axis, why is that an invalid case?
Yeah, so let's just try to do that. The point is you can't really draw the picture, right? So I'm not really sure. I'm trying to think about how to help you see that. But you see, maybe we'll look at this one. Let's say we have one axis. If we tried to shard them both, what data would be on which chip? Right?
Yeah.
I don't think you can quite say, right?
So yeah, I think that maybe I can think loudly and reason with it. Let's say we have a 2 by 2 tensor.
Yep.
And so which means that if I'm sharding the rows along all 4, let's say, then 2 will not fit. Let's say 4 by 4.
This is a 2 by 2 tensor and a 2 by 2 array, a 1 2-dimensional array. And let's just try to draw the picture right here.
So no, I think let's take a slightly different example. Let's have 4 by 4 tensor and the 2 by 2 array of devices.
Okay.
So basically what I'm hoping to achieve is that once I shard the row dimension of this tensor along 4, so this means that each device has 1 column only, let's say.
Is this okay? I'm giving you a row each.
Yeah.
Okay.
And then since the second dimension is also sharded across 4 of them, then the row of the same color also gets further divided among those 4 devices. So essentially, it will be like green and red, blue and yellow.
So I might have gotten more than I bargained for trying to draw this for you.
So
And you want a permutation here?
yeah, so I was just thinking that and I'm also thinking loudly here. I don't have this very clear on my mind exactly how this works, but yeah, something along those lines that you just
Yeah, I
did.
mean, I think that is an interesting question of how you'd represent if you wanted a tiling like this, how you represent it in JAX.
And by the way, I don't know of any real case when I would actually want to do that. So this is completely hypothetical question. It was just my curiosity that how, like, what is an obvious way to think that it is a not valid scenario? So that's what I was trying to get
Well, I
at.
think it's underspecified what you mean in this case. Is kind of why JAX is rejecting it.
Okay.
But you drew that tiling, but there are other tilings that you could imagine. Oh, Fairbanks, what's up?
Oh, hi, it's me, Sky. If you wanted to do like a really crazy sharding like that, you would probably use a positional sharding. So how I think about this, like forget what a positional sharding is, but like basically a sharding is a way to say, I have my data array, I'm gonna slice it up into little pieces, and then which piece goes on which device. And so from that specification, you could do whatever you want. You can have like a crazy checkerboard or anything. What the name sharding does is like usually we don't want such like a crazy precise sharding. Usually we're doing this common pattern of taking the physical devices and turning them into this mesh and then mapping axes of the array onto those physical mesh axes. So this is like a constrained representation of a sharding. It's just one that people find very useful in practice. So yeah, there are definitely shardings you can imagine that are like very difficult to express with the mesh and named axes paradigm, and that's kind of intentional. Like it is a shorthand for like common use cases.
Yeah, thank you, Sky. And yeah, and just thinking through, I think it does make sense that why it rejects. I was not able to imagine at first place, so that's why I was just going through that thought exercise. And thanks for humoring me with that, Rafi. Please go on.
Well, I'm glad we have Sky here to keep us honest. And Matali, I realize there's one more thing I should give you as context here, which is we could also, instead of making a 2x2, we could make a 1x4, which is the same number of devices as we originally had, and then the use of my axis 2 will basically have no effect. So that's another way you can think about it, where we can have now a 2-axis mesh, but it's really a 1x4, and actually nothing has changed. We just have a singleton axis that really doesn't have any meaning, and that's in this case my axis 1.
Got it.
Cool. And I guess the final thing I should do, and Sky, tell me what else you think we should do here. But I do think we should just show you that we can in fact do math over these tensors. So I'm going to before I answer questions in the chat, I'm just going to quickly help us do a little bit of math. So we'll make B be another one of these. We will make a second partition spec, which we will just make in some other totally arbitrary way. And then we will, excuse me, P1, P2, sharding A1, sharding 1, P1, cool, sharding 2. Perfect, A1, A2. And we can in fact add these two tensors, even though they are sharded differently. We can get output equals sharded A1 plus sharded A2. And then we can see output shape and we can see output shards. And actually, it's not clear a priori how output will be sharded, right? So that's something JAX is deciding for us. And JAX chooses this convention, but JAX is trying to find an efficient solution here. And then, of course, this also works in JAX-JIT. Cool. Dialog flow.
Do these concepts also apply to higher dimensional tensors?
Absolutely. So we actually can't visualize them as easily, but there's none of this depends on anything about A's shape. So I will just tear this one down, and it goes exactly the way you'd expect. So we can do a device put, we can get rid of this and this. All right, and then we get shard A1, and we can have a shape. And I believe that last line won't know how to visualize it, but we will. There's no reason there has to be the same sizes. So excuse me, I didn't change the size of A for you, but we'll make A for you, and then the exact same code will work, and we'll shard the same way. So here we set to shard over the first axis, right? Because we took my axis 2 in the second position, then we put that axis in the first axis of the tensor, and indeed the overall tensor, which is 1024, 128, still that size, but each shard is 256, 1024, 128. So there can be like a total mismatch between the size of your mesh and the size and the number of dimensions of your tensor, the rank of your tensor. Cool. Any more questions about how sharding works? If not, we're going to hop and try to talk about some math. What shardings are efficient?
Hey, Rafi, I have a question, actually.
Yeah.
Ben. So it makes a lot of sense when you know which rows and columns are going to be on, which computation of rows and columns you're going to be doing, because you can set it to the same machine. But what if you're doing something like a convolution or something, which requires like a mix? How do you think about things like that?
So we're going to do matrix multiplication then next. And I think that has the same property you're talking about, where it's not embarrassingly parallelizable. So we're going to have to communicate across chips.
I see. Okay, that'll be cool.
Well,
yeah, I'll
matrix
put that to that then.
Perfect. I mean, all the questions are spot on. Cool. I'm going to get started on discussing the math. Okay, we have this picture. So in an LLM, we have a very specific structure that we're typically interested in. So we have activations on the left. We have activations on the right that come out. We have weights. And what we will add in kind of an additional constraint, which is we want to be able to shard the left and the right the same way, because we want every layer to be sharded the same way. But then the weights can be sharded differently. And then additionally, there's really important structure. We know the weights in advance for the whole computation. There might be 100 layers in this. We know all of the weights in advance, but we get the activation layers only after we've completed the previous layer. So that adds incredibly strong structure onto this problem. So there are a couple different strategies. So again, I'm going to use this language where we have two devices. We shard over what axes we choose fit. Yellow means replicated. And then we get applet. This is one example solution. And we can discuss it. In what case is this solution right or wrong? So this one we call activation sharding, because we're sharding over the activations of the tensor. This one is called batch or data parallelism, where we're sharding over the batch axis. So this is the kind of like the simplest solution. And the reason why this solution is so simple is actually exactly what Ben was saying, that this is a fully separable problem. So we can separate on this axis, and each chip can do the computation on its own. So data parallelism, very, very like attractive, very, very simple, practical solution. But it ends up not working pretty quickly. So one example is that GPT-3 is 175 billion parameters. A 4-byte parameter that requires 700 gigabytes just to store the weights, just to store these things for GPT-3. And each chip only has 32 gigabytes. Even the biggest chips nowadays have 95 gigabytes. So you can't fit GPT-3, and then you definitely can't do any other useful computation. So what is our next option? So if you remember, we had the system diagram, and basically we've overflowed this HBM. And the question is, like, where else can our chip turn to for help? And the answer is, well, there are two places it can look. It can look over PCIe, or it can look over interchip interconnect. And actually, the interchip interconnect is a lot richer, right? This is a 30 or 40x speed up on interchip interconnect. So we're going to think about using the interchip interconnect next. And what this is telling us, this calculation is reminding us, is for every byte that we read over the interchip interconnect, we need to find 1,018 flops to do, or else we're going to be ICI bound. We're going to be interchip interconnect bound. So the first trick, and it's kind of like the canonically the most useful trick actually, is we shard both the batch and the weights. And then we do the following algorithm. While we're working on layer I-1, we actually just do data parallelism. But while we're working on layer I, we do an all gather. So we take these sharded weights and we unshard the weights. So we go from every chip having its own to every chip having different. Then we do the matmul, and then we can forget about those weights. And it kind of seems crazy that we're just reproducing this embarrassingly parallelizable case. But the really key structure is that there are 100 layers in a row that we're doing. So maybe 200 matrix multiplications, roughly. And we only have to have the weights for the layer we're working on in each chip. The question is like, when will this work? So just to remind ourselves, the number of flops in the matrix multiply is 2 times batch per chip times e squared. So let's just remind ourselves that, right? Batch per chip is the left dimension, e, e, e. So it's the product of the 3 dimensions in the matrix multiply. Batch per chip, so 2 times batch per chip times e squared. The all gather is going to require 2 times e squared bytes, right? So we have to read this thing, and we're going to say we read it in bfloat 16, so 2 times e squared bytes. So the arithmetic intensity works out to actually be able to cancel out batch per chip flops per byte. So really, as long as we have our batch per chip to be bigger than 1,018, we can fully stay flops bound and be fully embarrassingly parallelizable, right? So we at the same time we do these 2 operations, we are able to do the all gather faster than the matrix multiply. So we're able to stay busy doing the matrix multiply the whole time. So that's kind of the magic of FSDP. Cool. And some questions in the chat?
Yeah, I was
Susie.
wondering where this factor of 2 coming from?
Yeah, let's look at the various factors of 2. That's a good question. Which factor of 2 is bothering you?
For example, 2 times e squared. I see like the elements in the weights is like e squared. Why is it 2 times?
Okay, I'm assuming that we're getting the weights in bfloat 16, which is 2 bytes per parameter.
Right.
So that actually they happen to cancel out. So you can, and like honestly, for the purposes of this class, like feel free to ignore all the small constant factors. Okay. But yes, that's where that one comes from, and then this one comes because there's in the past we've kind of talked about it maybe just a little bit, but there's 2 times dimension 1, dimension 2, dimension 3 flops in the matrix multiply, because there's a multiply and an addition, so we count that as 2 flops.
Okay, thanks.
Yeah, great question. Any more questions? Cool. So jumping on to the next one, eventually FSDP stops working for like a lot of different reasons. One is very big LLMs. So eventually, for example, a sequence will just get too long. So the sequence, if it's like 65,000 chips, that might be more chips than a single FSDP replica can handle. There are actually a number of reasons why in practice FSDP breaks down, but FSDP, this fully sharded data parallelism, is the most useful idea in the field, and it's like kind of the first solution for lots of things. And then for inference, FSDP doesn't help. Cool. So going on to tensor parallelism. So here we do the opposite sharding on both the activations and the weights. We do the same sharding on both sides, and now the computation is not embarrassingly parallelizable. So what happens is if we do the matrix multiply locally, we'll get outputs of the right size. So here I've drawn them as being this tensor over here, 1, 1, 2, 2, 3, 3, 4, 4, and the same over here, but they're locally the right size, but they're the wrong contents. And we have to have them all be added together to get the right results. So again, this is actually much harder to overlap than FSDP, but the same principles apply. We need to compute the first row, and then after we've computed the first row, we can do this adding operation and fix it. Then we compute the second row, and then we can do the adding, and then we do the third row, and then we can do the adding, and then we do the fourth row, and then we do the adding. So if you have 4 pipeline phases, since they can be overlapped, it would take 5 time steps to do the work of 4. So you would be at 1.25 as fast. As you make those chunks smaller and smaller, you can exactly get to the matrix multiply time. You can be entirely flops bound while doing this. Cool. And then there's the same calculation. So now the number of flops is 2 times batch times e squared. So I've done it now global batch, divided by the number of tensor parallel shards. Good, because the batch is global here. So we're just dividing by this batch axis. The amount of communication actually doesn't depend on the number of participants, because we have to do this whole reduce scatter either way. So this is actually the same amount of communication. We always have to communicate 2 times batch times e. We'll discuss that more in a later session. To do that reduce scatter, to do this operation will always cost us 2 times batch times e. So as long as we can keep e over num tensor parallel shards bigger than 1018, this solution is going to work well. So it's again kind of a second option. And someone has their hand up? Yeah. So in LLM training, Jason asks, batch per chip should be sequence length into consideration. Yeah, absolutely. So for this math, we've skipped talking about sequence length because we were just talking about the map mols. And what we mean by batch per chip is the batch per chip in tokens. So if you have a sequence of 1,000, that counts as 1,000 tokens. Awesome. And now I will do just showing us actually the best strategy. So tensor parallelism is basically almost always less attractive than FSDP. So if we're going to do one of them during training, it will be FSDP. But we're actually going to see that the hybrid strategy works best. So here, again, I'm assuming it now a 2D mesh. We shard both ways. And now we combine both ideas. So we do the all gather ahead of time. And then we now have the same situation we had before. And we can do the online collective map wall. So I've worked out both of these. I'm just assuming we split our bandwidth. And this is going to work best in a regime where E is greater than, now it's 2,000 times the number of tensor parallel shards. And the number of tensor parallel shards times the batch per chip is bigger than 2,000. So the key kind of observation here is that the members of the tensor parallel share their batch. And one of the really, really important things is this in practice is a much softer constraint. It's kind of quadratically easier to satisfy. So I've shown a couple examples below that show actually this approach works great in practice for if you have a fairly small batch size and a fairly large model. Cool. So before we go, that's the last of the analysis. So I'm going to do like one more dangerously live demo. But any questions before we get there? Cool. Should have gotten this one more prepared. Awesome. So what we have kind of handy here is a script that lets us exercise each of these. Maybe I should show us our script first. let's just exercise each of these dimensions. So this is the same things that we've seen before. So here, the script, and I'll post it in the notes after. Let's just pass in each of the different things we're interested in: profile path, embedding, batch size, number of layers, DTN data parallelism. So it can do data center networking as well. But we mostly care about ICI. So that's an interchip interconnect. And then it will just do the matrix multiply. So it'll time it for us. We saw that from a previous session. And it will just do the math for us. So it will create the layers, and then it will multiply the layers. So this is exactly, we, for whatever reason, have a sigmoid instead of a ReLU, but it doesn't really matter. It's the exact same logic. We're just multiplying the two matrices. So what we'll do here is, let's just maybe see if we can run it by default. We're going to try the different settings, and we should see that we're able to get good performance. So I will make this a little bit bigger for folks. Okay, and we can see that our teraflops per second per device is 269. So in principle, the system is capable of 275. And that is so pretty good that we're getting 269. So I think that this is defaulting to FSDP parallelism. So let's just, yeah, so that's the default. So we have FSDP parallelism. And if we, so let's put all of these numbers in. FSDP parallelism for ICI tensor parallelism is 1. And then we should probably have our batch size. So our batch size in this context is our batch size per chip. That's what we're doing here. And then we should also, I guess we should put in the, if we can find it, we can put in the, so we 496, and then we should put in the size of our matrix multiply, which will be embedding dimension. And we'll make this some big number. That might be a little too big, but cool. So hopefully this will show us we get good performance because our batch size is 4096. So 4096 is big enough that we should be able to get reasonably good performance. So actually not perfect performance. I guess 4096 is a little bit close to that limit. So maybe we should. And what we can just see here is that this is a regime because we're just a little bit close to that limit. Where going to tensor parallelism will help. So we get 189 with batch with here, and then hopefully with tensor parallelism we can go a little bit higher because we're further from the limit. And then we'll additionally show that tensor parallelism works well in the small batch size regime. Okay, so indeed tensor parallelism works well here. Hopefully tensor parallelism will also work with a smaller batch size. Sorry, I meant to do 1024. So again, tensor parallelism should work with a smaller batch size because again, it doesn't, the communications don't really, the arithmetic intensity does not depend on the batch size. So again, tensor parallelism does really well, but now because we made the batch smaller, FSDP will do even worse. So we can do that here. And that's all good. So we were able to get good performance in this for this particular problem with tensor parallelism, but not with FSDP. So we only get 100 teraflops per second with FSDP, so not doing as well. And then the other thing I want to highlight is like this isn't a panacea. So if we make this like 2048, neither of the solutions is going to work fantastically. So this will be close because now we're actually very close to our arithmetic intensity limits on both embedding and tensor parallelism. So we get 100 teraflops per second when doing FSDP. And we'll see how we do on tensor parallelism, but it's possible, obviously, to have problems which are basically too small for the interchip interconnects to handle, and therefore we can be unable to, even extracting all the parallelism in the problem, we might get bad performance in both cases. So in this case, we get pretty bad performance, 130 teraflops. We're calling 270 teraflops is good on this platform. But all the solutions are going to give us bad performance here. And I think we might be able, actually this might just crash, but we might be able to try a hybrid. And in general, that hybrid is good. I don't think it's actually going to do too well on this platform for some technical reasons, but we can see it here. So unfortunately, there's some reasons why this won't work well that we'll see later on. But this problem basically, now that we've made the size of the matrices basically 4096 by 2048, it's too small for us to get good performance on the TPUs, and we end up getting bad performance, even though a single TPU can do well. And that's kind of like to Ben's point. When once we lose embarrassing parallelizability, we really have to think about the performance of those communications.
Hey, Rafi, I got a bit of a dumb question for you.
Yeah.
We're deciding, XLA is deciding whether to do FSDP or tensor parallelism purely by which axis we annotate. So what is to stop XLA from just deciding to gather things in the other direction, to gather all of the activations to where the weights are striped, for example?
Yeah, I mean, they end up being slow. So that's a really good point. So within the computation, let me start by giving some context there. Within the computations in here, we use this with sharding constraint. So this is inside of a JIT. And we'll see this when we apply this to our own neural net. But the way, the same way we could put device put outside of a JIT, within a JIT, we give XLA a hint. Hey, use this sharding constraint. And then XLA honors those sharding constraints to the degree it wants to, but it can, as Zach is mentioning, violate that. So again, the computation follows the sharding to the best degree possible, but definitely not universally. So XLA can decide, well, like instead of doing it the way the way you intended, I have this sharding constraint on M1, I have this sharding constraint on M2, but I'll do this matrix multiply in some other way. And then to answer Zach's question, this one sufficiently constrained. This sharding constraint and this sharding constraint are sufficiently strict that that XLA can't find too good of an answer, following our rules.
Can we confirm that XLA has done the right thing in some way?
I mean, I don't. Actually, the right thing is something that I haven't. Is a little bit more complicated than I've made it in this class, I have to admit. So I actually I know exactly what it's doing here, but it's doing for these smaller ones, it's doing a slightly different algorithm because it's under so much latency pressure. So we can see it in a profiler. I think we'll see those in profilers for like the real, when we get to the real model. But does that make sense?
Yes, thank you.
We'll definitely want to do that for the real model. And I'm just curious, I want to show everyone we're high, and we'll also see these with sharding constraints in more detail when we apply these to the real model. But yes, if you put in the right sharding constraints, it's actually very likely to do the thing you intended it to do. And then the one thing I wanted to show you is actually here, I've put in these with sharding constraints. I just actually removed them, and we get actually very close to the same performance. So with sharding constraints is telling XLA, actually, please do in this intermediate representation, here's how I'd like you to do the sharding. But for this particular thing, with or without them, produces almost the same performance. So it's saying XLA is doing an excellent job of propagating the sharding constraints, of guessing how we should get tensor shard. So we get 130. If you let XLA guess, XLA gets 97. So we can do a little bit better than the compiler, but not too much better. Cool. That's actually all I had for today. I think that sharding is a pretty complicated topic. Are there any more questions about it? Cool. Well, then I'll just quickly say, echo Sky's point from earlier, that really the way to think about sharding is you have an array that's in all of your tensors, and JAX is just letting you think about it as if it's a big global array. So it's like those two representations are really the same, and JAX is giving us some semantic sugar, some convenience for thinking about this huge tensor that's sharded across so many machines as being a single object that we're able to use. Cool. Well, thanks everyone for joining. I'll turn the recording off, and if you want to ask some questions, please feel free to stay on the line.